For nitrate, the 100-inch telescope required 3 pounds of silver nitrate. Potassium hydroxide, this is not common ammonia. This is about 30% strength ammonia, or it's called strong ammonia water. Dextrose is the reducing agent that pulls the oxygen molecule off of the complex. It's not the only reducing agent that'll work. Formaldehyde will work, Rochelle salts works, fructose, inverse sugar, and a few others. But dextrose is easy to get. It's available at beer and winemaking supplies. That's what I used. The problem child will be the nitric acid now, because back when I was doing this in the early 80s, it was, before 9/11 and such, and Homeland Security, and you can still buy these kind of things. But now, if you don't have a commercial use for this, it'll probably be difficult to get. And because of the hazmat costs and shipping and stuff like that, you will need a chest full of money to get a lot of these supplies. One thing
Nitric acid concentrated?
About 70%. Yeah, technical grade's about 70% concentration. You can make silver nitrate very easily, though, since you have to buy the nitric acid anyway to do this silvering. When you react it with a troy ounce of silver, you're going to produce 49 grams of silver nitrate. You don't need a lot of expensive paraphernalia. I know the old texts talk about glass beakers and scrupulous cleaning of the containers and so forth and so on, but now you can buy these, plastic Dixie cups, clear, the crystal clear kind. They're chlorides free, they're grease free. Throw them away when you're done, and they're convenient, hold about 500 milliliters, so that's enough capacity for about a 10-inch mirror. Stirring rods you don't need. You can use plastic straws, same thing, clean of grease and chlorides. This is not cloth duct tape. It's two-sided. It's metal tape. It's used in ductwork. Different types of metals are available: aluminum, copper, stainless steel, among others. I just put the stirrer in there to show you that you don't need a stirrer. If you want to recover the waste silver, you'll need a few other things: a small graphite crucible, a furnace to put it in, and some pool acid, a little bit of borax as a flux. Everything except the dextrose can hurt you, especially your eyes. The eyes are your biggest part of the body to protect. The silver compounds can do a lot of damage to the cornea. If you get it on your skin, it just makes a black stain, usually lasts about 2 days, comes off. Some sodium thiosulfate will take it off if you get it soon. I did all my silvering barehanded. Why would you? Because when you're handling wet mirrors and stuff like that, with gloves on, they can get slippery. You can drop the glass. If you get a little bit of silver nitrate solution on you, it's no big deal. These are dilute solutions. In use, they're about 6% only. It'll just do some staining on your hands, but you won't lose your grip on the mirror. I always had face eye protection, though. And you'll read in some text about different explosive silver compounds that can be produced, fulminating silver and silver fulminate, or some silver amide. But you really have to be careless to have this problem. But they really make issue of it in a lot of texts. Now, like I say, you want to protect those eyes. And back when I was born in the 50s, they were using very dilute silver nitrate drops in the eyes of infants to prevent newborns infection, but because silver has a microbial property. You probably have heard about silver bars hanging in Roman wells for the same purpose, but now they have something that's probably more expensive, doesn't work any better. The potash will burn you, and the problem with it is it's very tenacious. If you get it on you, because it breaks down the protein bonds in your skin, and it's just hard to remove it. It's almost worse than acids, really, but you want to, anytime you're mixing up the potassium hydroxide, you need to have gloves on for that. This is basic, though, adding chemical to the water, not water to the chemical, because the heat that's evolved. It also fumes when you first mix it up. You'll smell it. The 30% ammonia is pretty caustic. You get it on you, it's hot. And it can damage your eyes just as bad as the nitric acid. So you want to do some time reading. Okay, the way you make up this solution is you react it with the nitric acid. This is 50-50 mix, this specific gravity 121. You take the 70% technical grade, which is a little bit too high a concentration. If you try to dissolve it in that, it'll just pacify the silver bar, and no further reaction will take place. So you have to dilute it a little bit with some distilled water to bring it to about a 50-50 mix. It's not real critical. 50-50, somewhere there is about. If you do the arithmetic, or you can go to an online percentage calculator and plug in your numbers of how much volume of 70% you have and what volume of 50% you want, and it'll tell you how much water to add to the 70% to give you the volume of each one of the 50% online calculator. When you make the, this is important here, don't drop the silver bar into the beaker of acid because it's going to splash up. You put the silver bar in the bottom of the beaker, and you use a beaker because you need to warm it a little bit to hasten the reaction. It'll give off a brown and reddish fumes. Those are nitrogen and dioxide and nitric oxide, both of which you don't want to breathe. So you need to do it under either a fume hood or outside. It'll take a while to, it'll take more time to dissolve the last 5 grams of silver than it did to dissolve the first 25 grams of silver because the acid's being used up. But it will dissolve. It'll take a couple hours to do it. Now, I'm going to pause here because too much to go into about how to remove the excess acid. It's easier just to describe it. You're going to have a little bit of nitric acid left over in the solution. The way you get rid of it is you mix up a little bit of potassium hydroxide, say a half a teaspoon potassium hydroxide and maybe 2 ounces, 3 ounces of water. And then you would pour off maybe, let's say, an ounce of silver nitrate that you've made into the solution there of potassium hydroxide. It'll produce silver oxide, which is a heavy precipitate and it's insoluble. So then you pour off or decant the water. You don't have to filter, just decant the fluid. Pour it back into the silver nitrate that you've made, and that nitric acid will react much faster with the silver oxide than it did with the silver metal, and it'll form a water molecule and more silver nitrate. And then you would add some more water to make up a convenient amount of about 250 milliliters. Stir, 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 and then if there's no more silver oxide grains laying in the bottom of the container, there's still a little bit of excess nitric acid left. So you would do it again. And you'll remove all the nitric acid that way, and you'll know it's gone after there is still some silver oxide in the bottom that just simply refuses to go into solution. You know you've used up all your nitric acid that's free and left over. Then add about another 250 milliliters of water to bring the total volume up to about 500 milliliters of silver nitrate solution. So now you have a known quantity of silver nitrate in a distinct amount of volume of water. And it's easy to do the math. You'll now have almost 1/10 of a gram of silver nitrate for every milliliter of liquid you've got. Then you'd make up some potassium hydroxide solution, about a 6% by 30 grams of potassium hydroxide in 500 milliliters of water. It's going to be getting warm. It'll cool off, but that's your potassium hydroxide solution. The reducer, use about 50 grams dextrose and about another 50 milliliters distilled water. These are convenient quantities. And that'll make a 1/10 gram per milliliter reducing solution. Now the amounts you need, I took for an example a 10-inch mirror. This stays the same all the time. It's 5 grams for every, it's the square inches of the mirror divided by 5 will give you the amount of grams of silver nitrate you need to produce the film. In this case, you would need 16 grams of silver nitrate. So you do the math, you know how many grams there are per milliliter? You take something like a syringe that has the graduations you're looking for and pull off that much silver nitrate solution, put it in one of those Dixie cups, and then the potassium hydroxide percentage is 66% of the weight of the silver nitrate. So in this case, you'd need 10.5 grams of potassium hydroxide. And the dextrose, the reducer, is 40% of the weight of the silver nitrate. So in this case, 6.5 grams. And then you would take this silver nitrate solution that you have a known weight that you need. You want to get a 6% solution, so you would add, in this particular case, about 104 more milliliters of water, and you'd have a total of about 270 milliliters of silver nitrate solution, and that's about a 6% concentration. You'd need about that much caustic, about that much dextrose, and this is a reserve solution made out of what I called the stock solution of the 500 milliliters that you started out with of silver nitrate. That's to keep you from failing the reserve solution, very important. Now what you do is, first you have to get this mirror very clean. A single molecule of grease can't be there because the silver is bonded to the glass by electron attraction, just like it is with metal deposition of mirrors. So you have to remove all grease from the glass surface. And when it was done with nitric acid, because it'll oxidize that grease molecule. First you do regular conventional cleaning, and then you would swab the mirror with nitric acid to oxidize it, rinse it off. Nowadays, James Lurch, the St. Pete Club, he built a vacuum chamber for doing aluminizing mirrors, and he was describing to me the method they use for electrically cleaning the mirror surface with high voltage discharge of some type, or baritol rays, or what baritol rays. That's what they found on the Happy Planet when and on LV-426, and Ripley had to beat up Mr. Spock, to drive the spores out of him. You know the story on that. Anyway, we can use nitric acid, and then you rinse the mirror and put distill on it. If you get the glass that's completely clean down to glass surface, when you tip it up, there'll remain a sheet of water on the surface that won't bead. It'll coat it, like paint. It'll stay on the glass. So if there's any residual acid, it doesn't matter anyway, because silvering is done in a caustic solution, so it's going to be, any tiny bits of acid is going to be neutralized by leftover caustic. Now, this is a temperature-dependent operation. It has to be carried out at about 60 to 65 degrees, so it's not something that lends itself well to the tropics. In the tropics in Africa, they used to use a technique called Martin's method, which is different, uses different chemistry, but it could be done at up to 80 degrees temperatures, but the film was not quite as good. That's why they did the silvering of the Hooker and the 60-inch mirror in May and October, I think, because it was cool. And if you read Professor Ellerman's discourse on it, they started in the evening Well, I don't think that was just coincidence, because the temperatures are cooling off in the evening. So they did this silvering in the evening, and then they polished the mirror and burnished it all through the night. So if you try to do this in warm liquid, the only thing you'll get is a bunch of white bloom and black sludge, and you won't get the film. After you clean the mirror, you have to keep it covered with distilled water. And I got to stop and say that the way they did the hooker was they had a sheet metal dam, a wrap that they put on the mirror, which was lined with wax-covered canvas, and they secured it to the edge of the mirror with 4 metal bands, and then they stuffed felt down around the perimeter of the mirror, between the mirror, the glass, and the dam, and then they packed in a wax coated cording to make a watertight seal around the mirror. What I would do is I would use that metal tape, and which is about 2 inches high, and put that around the perimeter of the mirror without a single crease or wrinkle. It has to be a nice smooth application, and that is pretty good for forming a dam around the mirror. And then, well, that's how they did it on the hooker, and that's how I used to do it with metal tape. So now the titration process is this. You got the mirror sitting there, it's clean, you got the requisite amount of reducing solution sitting there on it, and it's in a cooled place, and it's just there waiting for you. So now you would take the strong ammonia water, and you begin the titration with the silver nitrate. You add about, first, say a half a teaspoon of ammonia water to this, and it's going to turn colors. It'll look like weak coffee with some creamer in it. It takes a lot of stirring to do the Brashear process, because it's not easy to mix things on a molecule for molecule basis. So it takes a tremendous amount of stirring to get a thorough mix and a thorough reaction in this. You can't hurry the stirring at all. You'll get a weak coffee, and then you continue the ammonia addition with a dropper, stirring between each drop, and what you're watching for is for a solution clearing. It'll start to clear up. When it's about right, it'll have a gray color to it, and it'll have specks throughout it. You don't judge the color through the liquid. You judge the color between the specks. You have to look down into it, and you estimate its grayness between the specks. If you try to titrate and all color's gone, you've over-ammoniated. But just to be sure, when you think you got it right, you add a few drops of this reserve solution, which gives you an excess, again, of silver nitrate. Like I said, if you completely clarify it, you've way over-ammoniated. And what has been formed now is a silver ammoniacal compound. Okay, this is the part where the explosive thing comes in all the time. You have to add the caustic, the full volume of caustic, slowly while you stir it. You can't just dump it in there and stir it. That's where the problem comes in at. And all the texts make it perfectly clear. Add it slowly with a lot of stirring. You'll never have a problem really if you do it that way. It's people somehow can't seem to follow directions, and they just dump it in there and they start, and suddenly there's silver ammonia all over the place and all over them. That's where the hazardous part can come in at. But all the writers who write about this particular possibility stress the point that the likelihood of this happening is very, very low if it's done the way it's supposed to be done, slowly and with stirring. But they still, I guess, as a disclaimer, mention it. Anyway, it'll be a black solution now because silver oxide has been formed. And you repeat this ammonium titration, and this time it's going to start clearing. The color will be different. It'll be the color of the liquid will be about the color of a broom straw. And when it's about weak tea looking, that's about it. And remember, I'm talking about a lot of stirring here. And then again, you would put in a few drops of the reserve solution just to move it back over towards this excess of silver nitrate and no excess of ammonia. Ammonia is the killer. It'll stop the whole process. So now this particular compound, silver hydroxide ammonia, it's not a compound, it's a complex. It's unstable. It won't last long, maybe a few hours at best, but it'll self-degrade because it's an unstable complex. And it's ready to give up that oxygen atom to anything that'll take it. So that's what the dextrose does. Okay, so you pour this prepared solution on the mirror, and you rock it back and forth to keep the solutions in motion. And they used to have workmen on the 100-inch that would be rocking the 100-inch mirror around. And the dam height was 10 inches, and the solution depth was about 2.5 to 3 inches deep on the mirror. And they would do this, watching the silver being deposited on the mirror. You'll see a deposit happening. The solution goes through several color changes. First it's zinc black, and then it turns brown, and then you'll start seeing the silver surface on the bottom, and it'll start to clear up like water clearing, sort of like clarity of water, almost. And it'll look like black peppers all over the thing, which are silver colloidal silver particles. And you keep this motion of the liquids happening. They used to take wads of cotton, and the workers would be dragging wads of cotton across the 100-inch mirror to keep all these little black particles from adhering so much to the surface of the mirror. But with a 10-inch mirror, you can do the same thing just by motion. And if you do this too long, you're going to get a compound called bloom on the surface. This is like a white dusting. And you can look and look and look, but you will not find anybody that'll tell you what this chemical compound is, except that it's bloom, and it's a bad thing. So it's a judgment call when the film is thick enough. You can double coat it, like they used to do the mirrors on Mount Wilson. They would pour half the silver solution, the prepared solution, onto the mirror with the full amount of reducer, and let it do its thing and deposit the silver. And then they would throw the rest of it on there and keep the rocking motion up, and they call that double coating, which Professor Ellerman said gave the best results. So after you're satisfied with the thickness, which is going to be no more, 10 minutes is the long side. I'd say it's more like 6 to 7 minutes at 60 or so degrees. Then you dump it off, you tip the mirror, pour it off, rinse it off with distilled water. If you want to save the spent solution, you dump it off into a container. Leave the mirror up on the edge to dry, and then you can look through the back side with a 100-watt bulb. And if you got a good coat, it'll be opaque, just like a good coating of aluminizing. Get it back from the aluminizers. You can't see a 100-watt bulb through it. If the silvering's been done right, it won't show through either. And then you polish it or you burnish it with either, back when the guys were doing it in the 30s, microfiber cloths didn't exist. They used chamois. And you cannot rub this silver off by burnishing. I mean, it is on there. So they used to burnish the 100-inch mirror all night long with a 3-foot diameter pad, and they'd run it over the 100-inch mirror for 8 hours, burnishing and polishing and compacting this silver coat. But you can use microfiber and back it up with cotton. And if it's been done right, there's really not a lot of burnishing that needs to be done. It's going to be a pretty hard, bright coating. There's always a small amount of bloom, but not too much. It's just a light dusting. And I've done this. I found that worked real well, was coating the mirror with a thinned out layer of lacquer. If you're going to do that, you got to use gloss lacquer, because semi-gloss has got platting agents in it which mess up the clarity. So you would take lacquer, you dilute it with lacquer thinner to a really thin consistency, like water thin, dump it on the mirror, dump it off, leave it on edge to dry. It'll form a wedged shaped cross section on the mirror. There'll be color fringes from green to pink depending on the thickness of the coating, much like a soap bubble, because you have interference from one surface, the back surface, to the front surface. So you have that interference that gives you a color. But it really doesn't have a effect that I've seen on the image, other than when you look down in the mirror, it has a rainbow color on it. Now, in a lot of YouTube mirror instructing, they'll tell you to use sodium hydroxide instead of potassium hydroxide because it's easy to get. It's a common lie. When you're looking at these YouTube presentations, you're not able to go up there and look at this mirror that the person made and really critically judge it. And they're not trying to first silver a telescope mirror. They're just doing a gee whiz, wow, we look at this, I put silver on glass. But you can't really judge it from a computer screen of how well it turned out. The old guys never used sodium hydroxide. They always used potassium hydroxide. And I never got good results from sodium hydroxide either. Got a lot of bloom and a lot of sludge. Sometimes I got a good silver coat, sometimes I didn't. And if it was identical chemistry, then it would be identical rates. But it's not identical rates. It's 71% of the weight, whereas potassium hydroxide was 66% of the silver weight. So chemistry is not exactly the same. But that's the real reason for it right there. It's easy to get and it's cheaper. But if you insist on using sodium hydroxide, you will probably come to this same conclusion.
You know what this means? It means that this damn thing doesn't work at all.
Exactly. You'll say it doesn't work. How do you save the silver you used up? Add about 1.5 ounces of pool acid to the spent solution. That destroys silver fulminate, and it converts everything to the chloride. Then you filter that precipitate onto a coffee filter, wad up put a little borax in there with it, stir it around, roll it up into a ball, put it into the crucible, and bring it up to bright red heat. And after it fuses, you'll find a little silver button down in the bottom of the crucible. Take the silver button, throw it into some water to dissolve the borax, and you're back to metallic silver. You'll recover about 80, maybe 85% of the weight that you used. The National Bureau of Standards, which used to be called Institute of Standards, used to be called National Bureau of Standards, has got information on silver mirrors. And this is the website address for that abstract that Professor Ellerman wrote up, if you'd like to read it. And of course, there's quite a bit of information in amateur telescope make books also. Okay? Anybody have any questions?
Is the information in those books up to date, basically? Or
No, those are old texts. Those are old texts.
the technique hasn't changed at all?
The chemistry hasn't changed.